Welcome to the lecture on catalytic organometallics, part 13. Very often in literature you find the expression CH-activation. Well, we should discuss that term. CH-activation is a term used for, well, indeed, gaining importance. A label given to publications and it gains importance. Why is CH activation then that important? Well, very simple. You have, for instance, an alkane unfunctionalized with its CH bonds, and well, you have a reaction which transforms that into a functionalized molecule with a functional group, and the CH activation publications are very often connected with transition metal catalysis. And this transformation is, of course, important since hydrocarbons are cheap and functional groups in a molecule means that product has far more value. So it gains the prospect of industrial importance. And there has been, for instance, a suggestion that these label CH activation should be restricted to transition metal catalysis, since, well, also radical chemistry, radical halogenation is somehow CH activation. And, well, there are other reactions, for instance, a deprotonation. For metallation, you can also call a CH activation. Therefore, the importance is then a bit ridiculous. Well, however, I think the main problem is that CH activation is a label for here, is used as a label for a certain kind of reactions. On the other hand, it should be more appropriate for describing a mechanistic step. For instance, well, let's take cyclohexanone and let's add an acid to it, and the acid will protonate in equilibrium the cyclohexanone at the free electron pair, the X minus coordinated by a hydrogen bond, and of course, by protonating this molecule, you will increase the delta plus at the hydrogens in alpha position. You will activate this CH bond since it is more polarized, and you will activate it by simply increasing the acidity activated for the deprotonation as the next step. So this is, of course, mechanistically a CH activation. And there's no reason why you shouldn't call that CH activation. So this is the problem with that term. Very often you find an alternative expression. This is the CH functionalization. Of course, CH functionalization is an abbreviation for CH bond functionalization. Well, at least I see a small problem with this expression. You just can't functionalize a CH bond. After the functionalization, the CH bond is gone. Yeah? You can functionalize a molecule, but not a CH bond. Well, I think the better expression is CH transformation you transform a CH bond into, well, a functional group. And if you want to be more precise, well, okay, then just say transition metal catalyzed CH transformation. However, if you want to look up in literature the subject we are talking about, you just have to look for CH activation and CH functionalization, because those two terms are the most common within this context. And, well, clearly it is important chemistry. So, in palladium catalyzed reactions, we have also seen a few examples where CH bonds are activated. Well, this was in the context of cyclopalladation processes, and sp3 hybridized CH groups, well, tend to be the less reactive. Here, for instance, methoxy anisole with an iodo group. I think we have discussed that palladium catalyzed domino process, which starts with forming a palladium 2 intermediate with a palladium 2 in close proximity to the CH3 group. And in that case, indeed, a CH activation by the palladium is observed. A pallada cycle is formed, and then lots of more steps will occur, since the reductive elimination to a four-membered ring is, at least in this case, somewhat inhibited. And as you already know, the oxygen is not important in this case. It also works with a tertiary butyl group, and again a pallada cycle will be formed, which also goes into some domino processes. You can use these kind of reactions, reaction at a CH group, for forming direct forming cycles. If you form a six-membered pallada cycle, then it is easy that it undergoes, it will readily undergo beta reductive elimination, forming then a five-membered hetero or carbo cycle. Two examples for this kind of reaction. think both from the group of Keith Fang Yu, who found about 2005 or 2006 that this pivalinic acid is a very interesting, valuable reagent for activating this palladium catalyzed process at CH groups. Reaction is performed with 5% palladium acetate. You have 30% of this pivalinic acid or corresponding salts, while in this case you have cesium carbonate present, and of course the cesium salt is then formed. You need an additional ligand, usually one which is sterically rather crowded. Tris-cyclohexyl phosphine, 10%. That means 2 equivalents to palladium, while you need a solvent, mesitylene, and okay, you heat that up 140 degrees, 3 hours. And that 5-membered heterocycle is formed and has been isolated in 65% yield. Second example with the same reaction conditions. Cyclohexyl substituent, a methyl substituent. As I said, same reaction conditions as before. The reaction takes place at the methyl group after the oxidative addition of a palladium 0 into this carbon bromide bond. We will have, as an intermediate, this 6-membered pallada cycle and reductive elimination then delivers this isoindoleninone with a cyclohexyl group here. 88% was isolated. Slightly modified substrate, just missing that carbonyl group. So not an amide, just the tertiary amine. At least not the cyclization product is observed. Why? All this is simply explained, I think. We will have the palladium here, the electrophilic palladium here, and it will be coordinated by the free electron pair of that nitrogen, then stabilizing, in this case, the palladium 2 intermediate. Well, after a longer reaction time, you will presumably notice beta hydride elimination, forming iminium salts as intermediates, and then some decomposition reaction. Yeah? Well, the difference is here in this case the electron density here is diminished. Therefore, not the nitrogen will coordinate to the palladium, maybe here that oxygen. However, still an electrophilic palladium-2 will remain, which can undergo the insertion reaction at the CH3 group. And this is different to the situation here, where that free electron paired with nitrogen delivers already electron density to the palladium. What we will see soon in the next examples is the important role of that pivalinic acid moiety. This is best illustrated by intermolecular processes. For instance, imagine you want to synthesize this 1-phenyl-naphthalene. How would you do that? Well, the idea, of course, would be using bromo-naphthalene as one coupling component, plus that phenylboronic acid, palladium catalysis. Well, this is, as you know, the Suzuki coupling reaction. Well, and where do you get this boronic acid from? Well, from the corresponding halide. So the initial CH transformation had been done by a halogenation process, electrophilic substitution at the aromatic system. Of course, it would be much nicer if you could just skip one halogenation and doing a coupling reaction, for instance, with bromo-naphthalene and just benzene. As you know, having a tether in between than performing the reaction intramolecularly wasn't a problem at all. The alternative would be, for instance, naphthalene plus bromochloroiodobenzene, and essentially the same process, palladium catalyzed. At least this one has been made possible after Fanyu found that pivalinic acid is an essential ingredient. So the reaction is possible with an 80% yield applying 3% palladium acetate, potassium carbonate as the base. You need a sterically crowded phosphine ligand, in this case for the 80% yield. It was this one. 2 cyclohexyl units at the phosphine and a dimethyl amino phenyl group as an additional substituent at that phenyl group. Okay, so as an additive, as I said, pivolic acid, abbreviated generally as PIV-OH, again 30%. You should have a huge excess of benzene in there. Therefore, this combination is one reason why this combination is preferred compared to that one. Then naphthalene should be solvent in the other case. Well, okay, so you want to have that in high concentration. Best would be having the benzene as the solvent itself. Well, you get some problems then with potassium carbonate and so on. Well, it's better to have a co-solvent in there. So they use mixture of benzene and DMA, dimethyl acid amide, in the ratio 1 to 1.2 as the solvent, and then the reaction works very well with the 80% yield. Let's have a look at the catalytic cycle. We have a palladium 0 as the initial catalyst. Again, palladium acetate reduced as usual. An aryl bromide oxidative addition reaction. I will omit additional ligands for clarity. That pivolic acid, of course, reacts with the potassium carbonate, forming the potassium salt. Potassium bromide is formed, and that pivaloyl substituents will be located at the palladium. Also suggested by calculations is this transition state with the aryl palladium still with a phosphine ligand present, of course. That complex will react with the benzene while that pivaloyl substituent will trap the proton . This is accepted as the preferred transition state. pivalic acid is formed, which will be then deprotonated again by potassium carbonate. And the aryl palladium with the additional benzene substituent. Reductive elimination gives the final product, the palladium 0 again, and it again goes into the catalytic cycle. So, next subject are palladium catalyzed reactions at CH bonds where no aryl halides are involved. Well, of course, we need palladium 2 intermediates, electrophilic, for reaction with the CH bond. Whereas in the examples we discussed here, you have the palladium 0 going into the oxidative addition, forming then the palladium 2. In the other cases where we don't have an aryl halide present, then we always need some oxidizing agents to reoxidize the palladium 0, which is usually formed within the catalytic cycle, reoxidizing that to palladium 2. Well, similar to Wacker type processes, but now we don't oxidize the C double bond, the olefin, but we oxidize as a net result a CH bond. So, and this of course also works better intramolecularly. So what we need, or what is a nice suggestion, and this has of course been done as a general scheme, we need a ligand, a tether, and there is then the CH bond. A palladium 2 is coordinated to that ligand. By the pre-coordination located in close proximity to the CH bond. Then HX is eliminated, generating such an alkyl or aryl palladium 2 intermediated, which is intramolecular coordinated here. This is not a Pallada cycle. It's better to call that a cyclopalladated complex per definition. So a cyclopalladation is this reaction until that stage. Then that X might be exchanged to something else, or the X itself is transferred to that carbon. Then we have this product as our final product of the reaction. Palladium 0 is formed. Well, and of course, this should be reoxidized to the palladium-2. So, let's have a look at appropriate examples. This benzoquinoline seems to be a model compound of choice. We will have that several times. So let's call that the model compound, model substrate A. Here a reaction which has been developed by Melanie Sanford's group. She's very active in this area. 2% palladium acetate, acetonitrile as solvent, 75 degrees, 12 hours reaction time, and, well, the oxidizing agent, we need 2 equivalents of that, is a iodonium acetate, that phenyl, iodonium bis acetate, and in that case you will get an acetate functionality to this remote position. So the palladium is coordinated here and CH activation takes place there. 86% yield. Another interesting case is the tertiary butyl pyridine. By the way, very easy to synthesize. Just take tertiary butyl lithium and pyridine, and it will react well. This reaction is a bit well, similar to the Chichi-Bobbin reaction, which you certainly will know. Same reaction conditions, but some more oxidizing agent is necessary to perform this CH transformation 3 times. This tris ester was obtained in 63% yield. Some more examples. Just the product. You see also other functional groups can be applied here in amide, and the acetoxy group is then introduced in the ortho position. This is preferred to the other ortho position. This would be more crowded, of course. 77%. azobenzene react in the same way. %62 yield. And now two more examples with the reaction taking place at sp3 hybridized CH groups. This amino group here as the ligand. The acetate is introduced at that position, 78%. And especially interesting is this one. In this case, the acetate functionality will end up in this position, stereo-selectively giving this product 81% yield. I think it's an interesting problem. Why is the acetate functionality group at this position, the same side at that hydrogen? Well, if you draw it like that, it looks like that hydrogen is in between that group and the former hydrogen which had reacted. So, well, you were right. We should draw the appropriate conformer of the starting compound. We have two annihilated cyclohexane moieties. These hydrogens in axial position. Well, okay, here we have the amino group, and then that hydrogen in equatorial position, the other one in axial position. And now imagine that the palladium 2 is coordinated here, then it's clear that it is coordinated in close proximity to this equatorial hydrogen. And this is activated there. Therefore, once again, substrate A, this benzoquinoline, isopropanol as solvent, some other oxidizing agent, for instance, a peroxo disulfate, and then an alkoxy group will be introduced. (72% yield). There are other protocols how to introduce a halide, even a fluoride in this position. But what about the arylation here? Again, substrate A, then an aryl halide, introducing a phenyl group to this position. This doesn't seem to work that well under palladium catalysis. The best seems to be catalytic amounts of ruthenium chloride hydrate. You always need to start with a hydrate because the dry ruthenium chloride is almost insoluble polymer. Triphenyl phosphine, sodium carbonate as a base, 140 degrees, 16 hours. You need a polar solvent. That N-methylpyrrolidone. And then you get an almost quantitative yield of that product. So in this case, ruthenium and also rhodium is definitely better than palladium. So we are almost done with our palladium chemistry. But of course, best would be if you could use substrates like A and an arene with no halide present, coupling that well, it is possible. With catalytic palladium acetate, well, if I remember it correctly, it's then 10%. That's not that nice. Well, but at least it works. You need stoichiometrically silver carbonate, DMSO as the solvent, 130 degrees, reoxidizing with paraquinone, and well, the reaction is not bad with 66% yield, but of course one hopes that this type of reactions having no halide present and combining then these aryl groups will be further improved in future. As I said, this is now we are finished with our palladium chemistry. In the next lesson we will go on with gold catalysis. Thank you for listening. See you next week.